So, what we will be discussing today is mainly how we go from the classical statistical mechanics that we were discussing till now to quantum statistical mechanics, where now initially we were describing the density, the phase density, like classically, but now we'll try to describe it in terms of the density matrix. And we'll see that while the concepts are quite similar, it becomes easier to deal with such kind of matrix representation when we deal with quantum mechanical system. So basically, we'll see how the density matrix looks for different ensembles. But before that, I'll discuss about the interacting systems. So we have seen what the canonical partition function or what the thermodynamic properties look like if we have free particles, okay, free ideal gas molecules maybe. But then now, if they are interacting with each other, what kind of changes do we have to do and what kind of modification comes into the equation of state. So first we will discuss that, and I'll discuss about van der Waals gases and critical what happens near the critical point. And then finally I would go to the density matrix and a discussion of density matrix. So that's how today's discussion or session will go. Obviously, I'll discuss these concepts. I'll discuss some preliminary problems and solutions. And if you have any doubt, you can get back to me. So to start with, we'll talk about this interacting systems. Okay. So we have used this concept quite a number of times that if we know the canonical partition function for one particle in some system, and then we can relate it to the canonical partition function for n particles using these relations when we have non-interacting systems. And this 1 by n factorial comes because of indistinguishability. But sorry, it should be to the power n, which I have missed. So it should be z dv1 to the power n by n factorial. Okay. So now that is for non-interacting systems. But then what happens if we have a interacting system? Okay. So here what we'll first discuss is there can be different kinds of interactions, but what we will discuss is mainly the pairwise interactions. So the pairwise interactions can be hardcore potential, where what we consider is one cannot penetrate into the particle. So if a particle has a radius of sigma, we'll consider that the potential from 0 to sigma, well, so here r is the coordinate which specifies the distance from one particle to the other. And so this tells you that for r from 0 to sigma, we have an infinite potential, okay, because we cannot get into the particle. It's a hardcore potential. And beyond that, beyond sigma, it's always 0. So one can have this kind of potentials, or one can have soft core potentials where you can see like there can be different kinds. So this is the Lennard-Jones potential, which is a well-known potential, but here this powers or exponents that we see here can be different for different kind of interactions. And depending on that, we'll have a different kind of V versus R plot. So we'll see that for a general potential for pairwise interaction, how does the equation of state changes. So before that, I would like to say that Kamalesh, did you do the class? Like, is it already done in the class? Then I would speed up. Otherwise, I would go step by step.
Ma'am, can you repeat?
So I was telling that I think this is supposed to be taught in the class. Whatever I'll discuss the theory. So is it already done in the class? In that case, I can speed up, or else I'll go step by step.
Ma'am, you can speed up, I think.
Okay. Okay. So you'll find this if you look at the class videos, I guess you'll find the same here. So the main point here is that uh, initially, if we have a free particle, we just have summation over I pi square by 2m. But now you have to include this potential term into a picture. Okay. So you have written it as V of R I J, where this means ith particle is interacting with jth particle. So it's a pairwise interaction. Now this V can be anything depending on your question. So we define uh, you can say a variable which is given as e to the power minus beta v minus 1 is equal to f of ij. Okay, and we'll see how we'll use this. So then this is how we write the normal partition function, right? So it's just the integration of e to the power minus beta h over the phase space volume. So here what we see is that the momentum terms come out because so that's quite similar to what we do for a free particle. What's different is that in free particles we integrate the position coordinates and we write it as v to the power n, right? But here we see that the Hamilton has a potential which depends on the position. So we have to integrate over the potential. So what we then do is now from here to here is pretty simple. So we divide by v to the power n and we multiply by v to the power n here and we will look at this integral. So here we have e to the power minus beta summation over ij, I less than j, so that we don't uh, double count the pairs, and then v of rij is the pairwise potential that the okay, that the particle sees. Okay, and then we write it in terms of uh, the product of pairs of 1 plus Fij. So this comes from this definition. So we replace this e to the power minus beta v by 1 plus Fij, and that can range over all values of I and j, all the pairs. So it's the product of the pairs. Okay. So what we then do is here you can see it's just we have just written this term 2 pi m kt by h square in terms of the thermal wavelength. And so this term is quite similar to what we see for a free particle. And now this is what is the new term which comes because of the interaction. So what we then do is this is your free energy. We know that free energy is minus kT ln z. So we put the expression for z here. And if we expand, this is what we get. Now here pressure is given as minus del F del V at constant temperature. This is known to us. So if we use this formula and do the derivative, we get something like this. So here what we have done is that this nkt by V, this thing, so whenever we write pressure for a free ideal gas uh, molecule, n number of molecules, we know we get P is equal to nkt by V, right? So the first term is similar to what we get for a uh, uh, non-interacting ideal gas molecule system, but then now we have this term. So here, this is the product of 1 plus Fij terms. So this term, this ln, so 1 by n ln 1 by Vn integration over the different position coordinates, product of 1 plus Fij, this is termed as F bar. Okay. And then you can see that now the pressure expression has been modified. It has this first term, which is the normal ideal gas term, but then we have this additional term. So we'll solve for F bar and del F bar del V and see what we get. So what we do here is that now we assume that the system is weakly interacting, which means the particles are quite far. So we are at a high temperature or low density. So that means in that case, if beta is 1 by kt, so at high temperature, this Fij will be negligibly small. So if we do that, we can ignore this higher order terms. So this product of 1 plus Fij over all the pairs can be written as 1 plus summation over I less than j Fij. And these are the higher order terms. Okay. So we put that here. And then what we get is the first term comes out to be just the uh, volume to the power n. Okay. Because it's 1. So if you integrate over all the uh, position coordinates, we get v to the power n. But the second term is something which involves this Fij, and Fij has the information of the potential that we are dealing with. So here what we then do is that if we consider only the first particle interacting with the second particle, then the corresponding term would be something like this, right? We'll have this F12 term. So that means F12 only depends on dr1 and dr2. So we can get the other position coordinates out of the integral. So we get a Vn minus 2, and this is the integration that is left. Okay. Now, in how many ways can we choose this pairs? We can choose it by NC2 ways. Okay. So in order to consider all the possible pairs, we multiply by the number of combinations, and that is NC2. And this is the integral for one such pair. Now here what we can do is we can go to the center of mass frame, where r is the distance between two particles. So there what that means is that we consider one particle to be fixed, and we see that uh, at a distance of r, if there's another particle, what is the potential that it sees. And so what we do is we take another coordinate, position coordinate out. So we get v to the power n minus 1, and we integrate over r, where r is the distance between the two particles. Okay. And f of r is, so now r is the distance, so we can directly we'll see that if for a given potential, we can directly substitute that here. Okay. E to the power minus beta v minus 1 is f. So we can substitute that value here. Then what is done is that now that was the value for that was the value for this integral, and now we substitute it in the expression for f. Okay. And then if we neglect the higher order terms, because we are in high temperature low density limit, so we get something like this. So if we put that in the expression for del f bar del v, and finally in the expression for p, we get something like this. So what we see that is that this is the ideal gas, like the first term corresponds to what we get for a non-interacting ideal gas system. But now we have this additional term. Okay. So here now if we write n by v as the density rho, we can expand pressure by this expansion. So this is called the virial expansion. And here the second term is actually the first correction term, and this is called the second virial coefficient. So the first virial coefficient corresponds to what we get for non-interacting system. And then the second term, the first correction on the second virial coefficient, gives us the first term that comes due to the interaction, and that is given by minus half FR dr. Okay. So that means for a given potential, we can just substitute the expression here and do the integration, and that would give you the second virial coefficient. So now it's clear till here, right?
Yes, ma'am.
Yeah. So now if we have a square well potential, what would be the second virial coefficient? And then you'd see, so here the question asks for the Boyle's temperature. So the Boyle's temperature corresponds to the fact where PV is equal to constant, or P. It that means the uh, so if you look at this expansion, that means B2, or the second virial coefficient, has to be 0 at Boyle's temperature. So first we'll find the virial coefficient, and then we'll see where, under what condition the second virial coefficient goes to 0. So what do you mean by a square well potential? It looks something like this. Okay. So less than sigma, it's infinity. Then it has some value for when r ranges from sigma to sigma prime, and beyond that it's 0. So if this is the potential that you have, what would be your second virial coefficient? So try to use this expression and find the expression for the virial coefficient. Can you try solving that? So what you have to do is, you know the expression for, you know what is f of r. F of r is e to the power minus beta v minus 1. And then in place of v, you have to substitute the values depending on the potential that is given here, and do the integration. So what do you get? Can you try solving it?
Okay.
Yeah.
I have doubt.
Yes, yes. Then
How we find f of r?
okay. So let us go to the definition of f of r. Okay. F of r is given by this e to the power minus beta v minus 1. Right. So suppose now what you have to do is, given the different values of r, according to the different values of r, you have different values of v, right? So you have to put that value here.
So for different values of v, we have different values of f of r.
Correct,
Or
correct. Because f has the so you are integrating in the formula LC, you are integrating over the entire space, right? So you have to do, ultimately the integration ranges from r equal to 0 to infinity. Now, given your value of V, or the interaction potential that you have, at different values of R, you can have different values of V. For example, in the question, so in the question, what happens is, for R less than sigma, your V is infinity. Okay. So that means when you write the expression for f of R, it will be e to the power minus beta infinity minus 1 for R ranging from 0 to sigma. Then from sigma to sigma prime, in place of V potential, it would be minus epsilon. And beyond sigma prime, it will be 0. So put that value of, so U here corresponds to the potential. So that is the V here. Okay, that is the V in this formula.
okay, ma'am.
Yeah. Are you stuck somewhere, or are you uh, okay? You are trying.
Ma'am, in the place of minus, sorry, uh, sigma to sigma prime.
Hmm. Yes. So there the expression for f will be e to the power minus beta minus epsilon minus 1.
Yes, ma'am.
So when you are integrating, your dr changes as 4 pi r square dr, right? Because dr, this is clear, right? So here dr in the first place is over, it's the r vector, so it's in 3D. Then when you change it to your spherical coordinate, it comes out to be 4 pi r square dr. So the, because here you are in 3D, and then you consider a spherical volume where r is the distance from one particle. Okay, so that means your integration will have this formula.
Ma'am, then the integration become a gamma function, something like this.
So see, in place of f of r, you'll put different values, e to the power minus something. And then you will have this 4 pi r square. Now, for the first term, it will range from 0 to sigma. So when you integrate, you get some sigma cube by 3 kind of term. In second place, you'll have e to the power minus epsilon kind of term. And that is constant, right? That does not depend on
Or
the r, right? So you can get that out. Should we
can,
go? Yeah, yeah, tell me.
can you show the solution?
Right, right, yes. So, see, it's something like this. So what we have done is you have put different values of v depending on the different values of r, okay? And you have done a integration.
Okay.
Is the answer clear to you?
Yes, ma'am. It's clear.
Yes, right. So now once you have got the expression for the second virial coefficient, if you were set that you have to find the Boyle's temperature, what do? You put V2 to 0, right? Boyle's temperature means their P will be constant. So it won't have this expansion. So we'll only have the first term. That means V2 should go to 0. So in that case, you have to put V2 equal to 0 and that will give you a the corresponding value of the Boyle's temperature. So you put this expression to 0 and then this is just reorganizing the terms and then you get something like this. So this is your expression for the Boyle's temperature. Right. So, if you look at your assignments or the questions that is given there, you can find. So, suppose if you have some hardcore potential or any given potential, you can accordingly put the value of V here in the formula, right? Yeah, write the F accordingly, and accordingly you can get the value of the virial coefficient. So, so once you get the virial coefficient, you can also get the value expression for pressure. Okay, and from there you can also get the expression for the equation of state, right? So all these are linked. So if you have any interacting system with some pairwise interaction, you can put the value of v and accordingly find the value of f for the different distances from a particle and accordingly find the virial coefficient, and that will give you how your equation of state and all the thermodynamic parameters have changed from the non-interacting case, right? Clear till here, right? Okay, so I'll consider it's clear. So now what I'll talk about is van der Waals gases. Okay, so we know that this is your van der Waals equation, right? So now what is different from the ideal gas than in the van der Waals gas is that here we have taken into consideration two things. First is the correction for finite size, where we consider the finite size of the gas molecules. So the volume is reduced to V minus B, where B is actually related to the total volume occupied by the molecules. And then in the pressure, we have this additional A by V square term, which comes because of the intermolecular forces. So here, if you look at the origin of these forces, so you'll see that, so it's because there is some interaction between these molecules that, so on the surface of the particle, the force or the net force acting on the molecules which are on the surface is different from what happens when they are inside, deep inside the bulk. Okay, that's because inside the bulk they are balanced. So if because of the cohesive forces, different molecules are interacting with each other, so the net force on a molecule in the bulk is actually zero, or it's balanced. But then on the surface, on one side you don't have anything. Okay, you have molecules only on the so below the interface. So because of that, there is a net force, unbalanced. Okay, where is my? So it's an unbalanced cohesive force which is directed inwards. So because of that, that induces a effective pressure. So the uh, what happens is that because of that interaction or the inward pull, the momentum with which the molecules will strike the wall will be less. So that's why your P ideal is actually the P original or the P real plus some term which comes because of this interactions. So if you look at, that means if you include this here in the expression, this is your expression for ideal gas. So if you put that here, you will have this P plus Pi term. And now if you have to evaluate or compute Pi, you'll see that it depends on the force. So the force acting on a molecule will be proportional to the number of attracting molecules in the gas. So it's proportional to the molecular density. And then it is also proportional to the number of molecules striking per unit area. So that means the net force, or from where we can find the actual pressure, is proportional to n square. So it has this n square by v square dependence. Okay. So that means if you consider Pi to be proportional to 1 by v square, you can write it as A by v square, where A is a constant proportional to square of number of molecules. So that's how you get to this expression, which is a modification from the ideal case. Now, keeping this point in mind, that what is the origin of A and B, if you are said that this is your Van der Waals equation for 1 mole, what would be the equation for n mole? Can you tell me the answer?
Is it D?
Okay, so if you say D, why do you say D?
For n moles, we have n or P.
Right. So the volume changes by n into B,
Yes,
right? Because the volume occupied by the molecules changes in by n into B. Fine. But then don't you think that the interaction will also change? So if
yes,
you have more number of molecules, then the interaction term should also change, right? Because we saw that this pressure is proportional to n square by V square, right?
yes, ma'am.
So keeping that in mind, that means if you have 1 mole, if you have some value of interaction, and that which results in some effective reduction in pressure. So if you have n moles, that would go as n square, right? That comes from the argument we just discussed. So that means for n moles, the expression would be A, right? Because here your A has changed to A into n square, and then your volume has also changed by n times. So this is your expression that you get for uh, n moles of uh, of Van der Waals gas, right? Is this clear?
Yes, ma'am. Yeah.
Right. Okay. So now one thing that we should be knowing is the what is the origin of the critical constants. So this is the experimental graph that was obtained, the isotherms for carbon dioxide that was obtained by Andrews in his experiment. So if you look at the theoretical data, you'll see that it differs significantly in this regions. Okay, you have this multiple, uh, you can say, so there'll be multiple roots of the so if you look at the van der Waals equation, for one value of P, you can have three roots. So depending on that, so for one value of, so there can be three roots. Depending on that, in this region, you'll have, so theoretically, you'll have a crest and a trough. But then those regions are actually, they are physically not uh, stable. Some regions are metastable, some are hypercooled or undercooled, so accordingly, or superheated. So depending on that, experimentally, we get something like this. So what is critical temperature or critical point is this point P here, where beyond which we only get the vapor phase, beyond which the liquefaction is not possible. So if you look at the plots here, you'll see that at the critical point, del P del V and del square P del V square goes to 0. So that means if you are asked to find the critical point, what you can do is, given your equation of state, you can do del P del V and del square P del V square and set it to 0. And that will give you these two conditions. And then from these two conditions, you can get something like this. So when this condition is satisfied, your volume becomes the critical volume, temperature becomes the critical temperature, and pressure is the critical pressure. So now if you solve for Vc from here, you would get something like this. Then if you put the value in one of the expressions, you can get the expression for the critical temperature, and that will be something like this. And with the values of Vc and Pc, if you put that here, you would get the expression for the critical pressure. And that's something like this. Okay. So you should have this idea about what is the critical point and what are the different values of volume, temperature, and pressure at the critical point. Right. But now what happens at the critical point physically is that here the properties of the two phases, the liquid or the vapor phase in this case, it becomes identical. Okay. So that means that initially what happens is, if you have a liquid phase and then if you have a vapor phase, there is a meniscus that or a interface that differentiates the two phases. But now when the properties of the two phase becomes identical, this meniscus disappears. Okay. And in this region, the compressibility of vapor becomes infinite. And the property, one of the, in like, it's a very well known property that is visually seen at the critical point, is the critical opalescence. So what happens here is that because the properties of the two phases become identical, at this point there is, so if you pass a light through it, it will not be transmitted, it will rather be, so the absorption increases at this point, the scattering increases at this point, and because of that, it becomes opaque. Okay. And if you go to a higher temperature beyond the critical point, again it would become transparent, but then it would only be in the vapor phase. So the critical opalescence is explained by the strong density fluctuations at the critical point. Okay. And because of the sharp change in the refractive index and the absorption coefficient of the medium changes, light is strongly absorbed and scattered, and that results in the solution or the system looking to be seen as opaque. Okay. So this is just to have the idea that this is what happens at critical point. Okay. So so you can have different questions depending on different systems about critical points. So you should remember what happens at the critical point in general, and then you can always use this relation that del P del V and del square P del V square is 0, and accordingly you can find the critical coefficients. Okay. So that was about van der Waals gas and the interacting systems. Now we would move towards the quantum statistical mechanics. So before we start with the formulation of the density matrix and the quantum stat, let us look at the basic concepts of bracket representation in quantum mechanics. So we know that in quantum mechanics, we represent a system. We can represent a system by some wave function, and then the observables is represented by some operators. Okay. And then what happens when you measure or do a measurement? So doing a measurement means operating by some operator. Okay, so when some operator operates on this wave function psi, what happens is you get a n psi n, where a is an eigenvalue of this operator and psi n is a eigenvector or eigenstate of this operator, right? So, and then if you have to find the probability of getting one particular eigenvalue or probability of being in one particular eigenstate, you can get it by this inner products. Okay. Uh, yes, right. And then when we do the time evolution of state, you use the Schrodinger equation, the time dependent Schrodinger equation, which says that IH ka del psi del t is H psi, where H is the Hamiltonian operator corresponding to total energy of the system. And then if you are given some operator A or some observable A, and you want to find the expectation value with respect to some state psi, you get it by psi A psi, and then this is for normalization. Okay. So that means if you expand that, you get something like this. So an is the corresponding or the different eigenvalues, and pn is the probability of getting this eigenvalue, and you do a summation over that to find the expectation value. So these things are clear to you, right? This is the basic quantum mechanics that we know. This is clear, and we will use this, and we'll use this concepts and describe the density matrix. All this is fine, right, till here?
Yes.
Yeah, right. So now what happens is, what is a pure state and what is a mixed state? Okay. So eh, whatever, suppose if you have some system, you can describe the state by some microstate or some wave function psi. Okay. But then in ensemble theory, or suppose in quantum stat or in statistical systems, you might not know what is your microstate. Even the microstate, even being in one particular microstate, can have some probability distribution associated with it. Okay. So in quantum mechanical system, if you are in a certain microstate, you know that you are in particular microstate, you can describe that state by some wave function psi, and then that is called a pure state. But on the other hand, if you have a system where it can be in any of the different microstates with some probability pi for each state psi I, then you are dealing with a mixed state. So depending on whether you are in a pure state or a mixed state, your density or density matrix or the density operator changes. Okay. So we now want to show that the mixed as well as pure states can be described by some matrix element of some operator, which we call the density operator. Okay. So we define that this is your density operator, while where rho k prime
Ma'am,
k. Yes, yes. Hello. Yes.
ma'am, the situation similar to the.
Uh,
Ma'am, can you hear me?
yeah, yeah. Tell me.
Ma'am, do the mixed state and pure state correspond to the superposition state and stationary state? It's like that.
It's not actually that. So suppose you have, so even a superposition state. So some state psi, suppose you have some state psi, okay? Now this can be in superposition of different eigenstates. So you can write psi as a1 phi 1 plus a2 phi 2. So then psi is actually a linear superposition of certain eigenstates depending on some basis. But even that can be a pure state, because you know that your system is described by this single, oh, sorry. Your system is then described by this single state vector or single wave function psi. So it's like, how do I say? So suppose you have two or three energy states, okay? And then you say that you are in a superposition of different eigenstates of different energy states, phi 1, phi 2, phi 3. But you know that state. So that state can be some a1 into phi 1 plus a2 into phi 2 plus a3 into phi 3. Okay. So that is a linearly superimposed state, but that state is defined, and you know that you are in that particular microstate. But then if you are not sure about what microstate you are in that case it will be a mixed state. Uh,
Okay,
i- so as I go forward, I'll give you some examples. I think that can clarify it even better. Okay, so let us go forward, and then if you still have doubt, you can ask me. Okay, so here you define the density operator by in some arbitrary basis phi k by this expression here. Okay, here the diagonal matrix terms, diagonal meaning when k prime is equal to k. So that is given as rho kk. Okay, so that is, excuse me, so that is given by this expression here. So that is the probability for the system to assume some special state phi k, right? But then the off diagonal terms, what do they signify? They signify the probabilities for the system to spontaneously make a transition from phi k to phi k prime. So according to how your system is changing from one state to another, or whether the system has some probability of changing from one state to another, or one basis vector to another, you can have different values of rho k prime k. Okay. And then this is how you are defining the density operator. So in this case, if you prepare your system in such a way that it may be in any of the states phi I with probability rho I and rho ik is 0, that means you can write this by this expression here. That means there is no interchange, like it's not changing from one basis vector to another, but it can be in different basis vectors with different probabilities. And then you get an expression for the density operator as something like this. Okay. So different states, different psi I, different microstates can come with different probabilities of rho I, and then it's a mixed state. But now if you are in a pure state, that means you are in one particular psi I. Okay. And then that is the state vector. So there rho I is 1 for one particular value of I, and all others are 0. So in that case, the density matrix becomes something like this. So this is the particular microstate by which you can define your system. You know for sure that your system is in this microstate. Now a microstate can be superposition of different states in some like superposition of different basis vectors. Okay, but you know for sure that this is your microstate. But if you are not sure about your microstate, so there can be different microstates with different probabilities, then that's a mixed state. Okay, so let me give you an example. Okay, so before the example, let us first discuss the properties, and then we will see an example through a question. Okay, so consider that it's a pure state. So that means your density matrix is represented by this outer product. Okay, this is the operator which is the density operator. Now the properties of the density matrix for a pure state is that now if you do rho square will be equal to rho. Okay, and then this is the Hermitian conjugate, so that is equal to rho. So rho conjugate is equal to rho. And then if you do trace of rho, so when you are doing trace of rho, that means, so n is some complete orthogonal set of state vectors. So that means the summation over n, outer product of n and n, will be 1. So if you use this relation here, if you use this relation here, you can write the stress as 1. So this is the normal definition of stress. So what you do is you do a summation over. So if you have some matrix, what is the stress of the matrix? It's the sum of the diagonal terms, right? So that means you do a sum over all the diagonal terms, so that you are doing a this inner product which involves n and n, so the same indices. So it's all the diagonal terms. But then what you can do is you can interchange the order of this terms. So psi, so then what you'll get in the middle is a summation over n, outer product of n and n, and that because it's a complete orthogonal set, that is 1. So that means stress of this pure state density matrix turns out to be 1. Is this part clear?
Yes, ma'am.
Yeah. And then when you define a expectation value of some uh, observable or some operator A, what you do is you find the trace of rho into A. And if you do that, you'll see that it's actually equal to the normal expectation value formula that we use, right? So we know that this is how we define expectation value, where psi are normalized already. So in that case, you can see that this is equal to trace of rho into A. That means here you don't need to know the individual states. If you know the density matrix, you can actually find the expectation value. Okay. So this is your properties of density matrix for a pure state. Now, if you have a mixed state, that means now you can have different microstates with some probability pi. Okay. So here again you can see that the conjugate is equal to rho. Okay, so so this property is same for both mixed and pure state. But now if you do rho m square, so m signifies the fact that it's for the mixed state. So here you see that rho m square is actually not equal to rho m. So given a density matrix, you can always do this check to see whether it's a pure state or a mixed state, right? And then again you find the stress of rho m and you get some. So here what you see is stress is again 1, but then trace of rho m square is not equal to 1 here, because rho m square is not equal to rho m, as we see here. And then if you find the expectation values, it goes in a similar way. So here you can just see that for a pure state, you had only this term. But now you are multiplying by the probability of being in each of that microstates and doing a summation over all the possible microstates. That gives you the expectation value of some operator. Okay. So now consider that you have a system of spin half particles, okay? And the state of the system is defined by this psi. So this answers your question, okay? So this is your psi. You know your system is in this state. But now that is actually a superposition of two. So this up and down are two eigenstates. If you consider some maybe sz vector, okay, then these are the eigenstates of that sz vector. So this is in some basis. So you can consider that it's some basis vector, and it's in superposition of these two basis vectors, right? But your state is well defined. This is your psi. So is it a pure state or a mixed state?
Ma'am, pure state.
Correct. It's a pure state because so a pure state can be a superposition of different eigen vectors or basis vectors. Okay. But you know for sure that this is your microstate. So this is a pure state. Now, how do you find the density matrix? Can you try finding the density matrix? So density matrix will be a outer product of psi with psi, right? Try to solve it and see what you get.
I get 1 by 2 times
Yes, 1 by 2 times. What's the matrix?
from the get Brava to upspin plus a get up upspin and draw of downspin plus a
So
get off.
first, right, right. All the four combinations, right? Are you getting all the four combinations? So outer product of up, 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 down, down, right?
Down. Yes, ma'am. In
Right,
get
right,
notation.
right. Then what you can do is, so you got something like this, right? What you can do is you can write this in the form of product of, so this is your column matrix of the two basis vectors. This is the row matrix, and then the one that you have inside, right? So this is your density matrix. The same, so whatever you have got here, that's how you, the same thing you have written in this representation, right?
Okay, ma'am.
So now this is your density matrix. So if you find rho square, you'll see that rho square is equal to rho. That tells you that this is, that proves that this is a pure state. So can you tell me what is the trace of the density matrix? Trace means the sum over the diagonal elements, right?
Is it 2 or
Hmm?
1 because a half vector outside?
Right. So it's half plus half equal to 1. But you can just tell it directly, whether like even you don't have to look at this thing. Why? Because this is the property of density matrix of pure state, or even if it is a mixed state. The stress comes out to be 1, right? We just saw the proof. So why is it 1 is actually because when you are doing a stress, you are actually doing a sum over all the possible probabilities, right? And that is always 1. So that's how this comes out to be 1. What you can try solving now is that you can try to find the eigenvalue of this matrix. You know how to find eigenvalues, right?
Yes, ma'am.
Yeah, if you try to find the eigenvalues of this matrix, what do you get?
Ma'am, 2. Is it 2? Lambda is 2.
So you have a half outside, right?
Okay. Then
So you are diagonalizing the matrix, and then one diagonal element will be 2 by 2, so it should be 1. What is the other diagonal element? All the, or what are the other, uh, so when you diagonalize, what do you get? What is the matrix that you are getting? So you understand the question, right? Your one diagonal element will be 1 by 2 by 2, that comes out to be 1. So that means one eigenvalue is 1.
the other one is -1.
Is it minus 1? So if you try solving, you'll see that one eigenvalue will be 1 and other will be 0. So this, or you can say on diagonalizing, you'll get something like only one. So this is in some, this row representation that you are getting, it's with respect to this basis vectors, right? Up and down. But then when you find the eigenvalues and the eigenvectors, what you will get is that this row takes up a form where only one matrix element is non-zero, and that is 1, and all others are 0. Okay, and that the corresponding eigenvector will be this. So that will tell you, that means, what does that mean? That means that only one state is possible, and the probability of being in that state is 1. So this happens only when you are in a pure state,
Okay, ma'am.
right? So what I mean is that one pure state can be a superposition of eigenvectors in some other basis, right? You understand? The up and down are some some basis vectors, okay? But then this state is well defined, and if you find the density matrix, and if you diagonalize that or find the eigenvalues and the eigenvectors, you'll see that this row has one non-zero dense matrix element, and that corresponds to this state, and all other values are 0. That means it is in this state with 100% probability, and that is what it means by it's in a pure state. Okay, now let us
Yes.
see an example of a mixed state. And I think that can, so here again, the trace is half plus half 1. Okay. But then let us go to an example of a pure state. And then I think the concept, so it would get clearer. So this can be a typical density matrix of, so what's different from the density matrix that you get here and what, what you get here? What is different? What's different here is that now this tells you that you can be in two microstates. One is a up state, another is a down state with probability half, with probability of each being half. So initially in the last question, you were in a superposed state, but that was the only state that was possible, only microstate. In this question, what this density matrix is telling you is that you can be in two possible microstates. One is a up state, one is a down state. So some microstates can be, so if you have an ensemble of microstates, what will happen in the last question? All the microstates will be represented by that same shine. But now here, what this tells you is that if you have an ensemble of microstates, some can be in up state, some can be in down state, and the probability that it is in up state or it is in down state is half for each. Do you understand? Can you look at the difference of the two cases? Is the difference clear?
Yes, ma'am.
Right. So this is a mixed state. So that means here there can be different microstates. There's only one possible microstate. Now in this question, so this is already, I have already answered this, that this is a mixed state because here two states are possible. One is up state, one is a down state, with each having a probability of half. Now what is the density? So if you expand this, what would be your trace, and how will your density matrix look? So if you write it in a matrix form, how will it look like? Try to write it in terms of that product of the matrix as we had done in the last uh, example.
Okay.
Yeah.
Ma'am, is it 1001?
Right. And you have a factor of half outside, right?
No, ma'am.
You don't have a factor of half?
Ma'am, but yes, ma'am, a factor of half, but inside it is 2002.
Okay. How do you get 2? So let us look at this example. So here, if you look here, you have similar kind of expression, right? So what is this giving you? When you will multiply here, you'll get, so this will give you up, down, and then again up and again down, right? Oh no, what am I saying? All wrong. Wait. So it should be up plus down. This thing, this when you multiply this by this, you'll get up plus down, and then here you'll get up plus down, right? And then you'll again multiply by the one that you have here. So what you get is the, this expansion. So here what you are having in the last question, what you had is that you don't have these terms, you only have this, right?
Yes, ma'am.
So if this is the state, what should be the thing, that this uh, cross terms or up down down up terms should go to 0, right?
Yes, ma'am.
Yeah, but you also have this factor of half outside, right? It's just a matter of calculations. I guess you are somehow missing the half,
Yes, ma'am.
right? So that means you get an expression of half 1001, something like this in the next question, right? You
Yes,
get
ma'am.
something like this, right? So what is this telling you? That your row is now half of 1001. So it's already diagonalized. So what are the eigenvalues in this case?
Ma'am, 1 and
Hmm?
1 and 1.
Wait, what is the, so from here, if you have to write the expression for the density matrix, what is your density matrix? Just if you look at this,
1001.
don't forget the half. See, when you are defining the density matrix, what is the definition? If you look at the definition, this is how you are defining, right? So for your question, this pi is half for both the cases, right?
Yes, ma'am.
So that term remains, right? When you write the, so here
Density.
when you find rho, what is rho? Rho is half into this term, right? Because this is so what is in between the product of the, the bra and the kit is rho. So the entire thing is rho. So you could have always written it like this term, then half into this matrix, and then this term. So that is rho. So rho is half into this, right? So similarly in this question, your rho should be half into 1001. Is this making sense? So
Yes, ma'am.
because see, physically, if you think, this coefficient or whatever coefficient you have in front of this each of these terms is actually the probability of being in this state or in this state, right? This like, so shy is a pure state. This is a pure state, right? Only if you look at this term, this is a density matrix of pure state for where the microstate signifies it's a up state. Are you getting my point? Suppose you, if you had a system where the only possible microstate is the up state, what will be your density matrix? Only this term, right? Only this term. And then it's a pure state. So there, the coefficient that we'll have in front will be 1, because you are in this state with 100% probability. Or suppose if you are said that your system, you are in, so the only possible microstate or the only state that describes your system is the down state. So that means your density matrix will be only this term, and the coefficient will be 1, because 1 is the probability of being in that microstate, the down state. But here you can be in up or in down state with some probability half for each. So this term, this is actually the PI term. This is the probability term. So that because if you don't include that, what happens to the stress? The stress becomes 2. That has no meaning, right? The stress should come out to be 1. So the coefficients take into account that probability. So you have to be careful about including the coefficients. So for this case, your rho is half, 0, 0, half. Clear, right?
Yes, ma'am.
Right. So what are the eigenvalues of the density matrix then? So if you have, uh,
Ma'am, is
suppose
it
if, yeah, so what is a eigenvalue? Suppose if you have some matrix, okay, some matrix which is given as, so you have this maybe, how do I say, lambda 1, this is 0, this is 0, and this is lambda 2, right? So then we know that the eigenvalues are lambda 1 and lambda 2, right?
diagonal elements?
Hmm?
Yes, ma'am, diagonal elements.
Yes. Why? Because when this operates on a, any parameter or any wave function, what you will get is lambda 1 terms uh, into the eigenvector corresponding to that, and plus lambda 2 into the eigenvector corresponding to that, right? So in this case, your eigenvalues, both the eigenvalues will be half and half. So what is that signifying? So what are the eigenvalues signifies? So what do the eigenvalue of the density matrix signifies?
Um,
It, yeah.
um, it tells each state with
Uh, uh, 1 second, I lost you. Yeah, yeah. Tell me.
degenerate state with
Degenerate state. Okay. What do you mean by degenerate state here?
two energy levels with the same
Right.
eigenvalue.
But uh, okay, okay. So what you mean is that the eigenvalues are same for both the cases. That's what you are meaning by degenerate, right? But what I meant to ask, that's correct. But what I mean to ask is that in general, what does the eigenvalue of the density matrix signify? So when you say that both the eigenvalues are half and half, what do they physically signify?
The probability of in particular microstate.
So the probability of being in this microstate is half, and the probability of being in the down, so up state is half and down state is half. That's what you got from here, right? The concept, like the physical concept is clear, right? What it is signifying?
Yes, ma'am, it's clear.
Yeah. So, and then when you do the stress, what will you get? Half plus half, 1. Clear, right? Now, suppose if you are said that, so, so what happened in the last case was that when you diagonalize this term, what I said is you will get only one non-zero term and all others will be 0, because then the probability of being in this state is 100%. That is what happens for a pure state. And in mixed state, you can have all possible combinations. So here in this question, you only have up, up and up, down, down. So you could have had other combinations where you also have up, down, up, and all of that. Okay. But what you will see in that case is that, so there will be different microstates with some different probabilities, but that would not be one microstate. Then it's a mixed state. When you have multiple microstates possible, it's a mixed state. Clear, right? Like you had this doubt of superposition and like that concept is clear.
Yes, ma'am, it's clear.
If you have a doubt, you can ask me.
No, ma'am, it is clear.
Correct. Okay. So now we'll talk about the time evolution of the density matrix. So initially we had seen that for stationary states, when we were talking about classical statistical mechanics, what did we see? We saw that in a stationary state where we consider that the phase density is not changing. So from the Liouville's theorem, we saw that for the space density to be constant, what happen, or for a stationary state, what happens is that rho has to be a function of h, that is the Hamiltonian. Similar thing happens when we think in terms of the density matrix. But now we will do it in terms of the, like we'll use the Schrodinger equation and the Schrodinger picture, and then that, which means that we'll consider the temporal change of the particular states. So what happens is, this is, each state follows this Schrodinger equation, and this is the Hermitian conjugate. And then if we consider that the probabilities Pi of each microstate do not change with time, so what do? We write ddt of P rho I is equal to 0. And then what is rho I? So ddt of rho I, in the sense that if ddt of rho I is 0, that means the probability of each microstate is not changing. What happens to ddt of rho? Rho is now the density matrix, the entire density matrix. So then we can substitute it here. And what we get is that IH cut ddt of rho, where rho is the density matrix, is given as Poisson bracket of H. It's not the Poisson bracket here, it's the commutator of H and rho, right? So this tells you that now for a stationary state where rho is not changing with time, what happens? H commutes with rho or rho commutes with H. So that means density matrix and Hamiltonian they have same set of eigenvectors, and in a way you can say that density matrix is a function of the Hamiltonian. So you get to the same concept or the same condition which we had got for the classical case. Okay, so now, so this is the general situation. So if we have to have a stationary state, the density matrix is a function of H. But now depending on different ensembles that we choose, the function will be different. Okay, so what will happen is, for a microcanonical ensemble, we know that rho n is 1 by sigma. So even in this case, what will happen is rho n, where so rho n is the probability of being in the different microstress corresponding to some energy E, and that is same, right? That is 1 by sigma. So that means in this case, each term of the density matrix will be a constant, and that will be 1 by omega. So that is the matrix representation of the microcanonical phase space density that we had seen initially. And what happens to the canonical ensemble? So this is your this is our classical representation. Now, when we write it in terms of in terms of the operator notation, so what we write is it is exponential of e to the power minus beta h cap, where it is the Hamiltonian operator, and then this is summation over n e to the power minus beta, and this is actually the partition function, and that because it's a summation over n, that means you are summing over all the diagonal terms, right? So in a way, it's actually the trace of e to the power minus beta h. So trace of e to the power minus beta h is actually your partition function. And then if you have some operator f, what is the expectation value? You find the expectation value as stress of rho into f. You know the matrix representation of f is some operator. You know the matrix representation of rho, so you multiply them and you find the trace, and that gives you the expectation value. So whatever you are doing now is same as what you were doing before, but now you are doing it in terms of with the representation of matrices. Okay, so that means now if you have to find the average energy, how do you do that? You do it like trace of e to the power minus beta h into h by z, which is the stress of e to the power minus beta h. Okay, and that can also be written as minus del del b del beta of ln z, same as what we had done before. So how do you define entropy? So entropy was defined as minus k ln rho. So here it would be minus k into trace of rho ln rho. So and then if you go to grand canonical ensemble, you have to include this plus mu by kt n term, which comes because now you can change or you can exchange particles with the surrounding, right? And accordingly, all the expressions would vary. This is clear, right? You're just going to the matrix representation. So whatever questions or whatever numericals we had been solving for canonical ensemble or grand canonical ensemble can be solved in terms of the density matrix by using this relations. So for example, if you have to find the canonical partition function for a quantum harmonic oscillator, so that means now your energy states are given as n plus half h cut omega. So how do you find the canonical partition function? You have to use this relation, right? You have to first find z, and then you have to find rho. So can you try to find z, and can you see what you get? You have to use this relation.
Which one? The row.
So what is z? Z is stress of e to the power minus beta h. And what is h now? H is your Hamiltonian operator now. And h can be written as n plus half h cut omega, right? For a harmonic oscillator. And n can vary from 0, 1 to dot dot dot,
From up to infinity.
right? So similar, like initially when we had done for harmonic oscillators using this relation, when we had used this relation, you can initially, like classically you can use this relation, right? So what you do, you write it like e to the power minus beta half h cut omega plus e to the power minus beta 3 by 2 h cut omega, like that you had written, right? Because en are the different energy levels, like the values of different energy levels, and then you did a summation over that gave you z, and correspondingly for each, the probability of each energy state was given as e to the power minus beta En by Z. That is what you did classically. Nothing changes here, only the representation now changes, where En is now replaced by the Hamiltonian operator. And then the phase space density is now the density matrix, which is now a operator.
Okay.
Yeah.
Ma'am, is it e power minus of beta h cross omega divided by 1 minus e power minus beta h cross omega?
Okay, that's okay. And then you have to, so it's just rearranging the things. So if you, so it's fine. Then you have to divide the numerator by the denominator, and then you'll get this sine hyperbolic function. So e to the power beta h cut omega by 2 minus e to the power minus beta h cut omega by 2, and then there'll be a 2 factor which will go up. So
Okay.
it's correct. You just have to use the hyperbolic function relations. So divide the numerator by the denominator and then use the hyperbolic function expression. So you will get this value. So this is similar to what you had done initially, right? So if you would have just done whatever we used to do for the classical case, it's similar to that. Just the representation is now different, right? And then if you find z, what would be your rho? Your rho would be something like this for each values of n, correct? So
Okay.
so depending, like this tells you that now depending on your system, so if you have a two level system, if you have, so if you have two level systems, your you have to, when you find z, you have to sum over e to the power minus beta e1 plus e to the power minus beta e2, and then accordingly you can find the different probabilities and the different parameters. So everything is similar to what we had initially done with the classical partition functions, but now so in cases of, in such quantum mechanical system, it often becomes easier to write it in terms of matrices. That's the only difference. Okay. So that's actually all for today. Do you have any doubt in whatever we I was discussing, or is it clear?
Ma'am, I have doubt.
Yes.
Ma'am, can you work it out the summation from n equal to 0 to infinity of that exponential factor? Yes,
Here, this thing.
yes, ma'am.
Yeah. So this is, so what will you do here is that so the first term will be e to the power beta h cut omega by 2 plus e to the power e to the power minus beta h cut omega by 2 plus e to the power minus beta h cut omega uh, into 3 by 2, right? Like that, okay? Then you take e to the power minus beta h cut omega by 2 common. So what you get is 1 plus e to the power minus half h cut omega and dot dot dot. So that is actually a geometric series, right? Infinite geometric series with the first term as 1 and the factor is e to the power minus beta h cut omega by 2. So then you will get e to the power minus beta h cut omega by 2 in the numerator divided by 1 minus e to the power minus beta h cut omega by 2, right? And then you divide the numerator by the denominator. Like you divide the numerator and the denominator both by e to the power minus beta h cut omega by 2 so that the numerator becomes 1.
Okay.
So what you get in the numerator, in the denominator will be e to the power minus beta h cut, no, e to the power beta h cut omega by 2 minus e to the power minus beta h cut omega by 2.
Yes, ma'am.
Okay, and that is actually 2 into sine hyperbolic half beta h cut omega. And you have this minus 1 because it's in the denominator. So this is like uh, I think in the third or fourth week when we were trying to solve the canonical partition function for different cases. So it's the same thing.
Yes,
Did
ma'am.
you get? Yeah, you got the answer, right? Huh.
Yes, ma'am.
So then for each energy state, P rho n is the probability of being in each energy state. So then you are using this formula, right? This is the formula that you're using. So in the numerator, you have the corresponding e to the power minus beta h term corresponding to that energy level. Okay. Any other doubt?
No, ma'am.
Okay. So I have a question just to check that you understood. So in the spin half state question, if you are just in spin down state, so what will be your density matrix? How will your density matrix look like in that case?
Ma'am, can you repeat?
So you have this spin like a spin half system, right? That we were doing some questions. So you have the similar system, but now you have said that your microstates, like you are in a microstate with spin down. Like you are in spin down. The microstate is such that the system is specified by the spin down state. So what will be your density matrix? How will your density matrix look like?
Ma'am, ma'am, with the minus 1.
Okay, why minus one? Oh, so see, it's a density matrix. So it will be a matrix. It won't be a number, first of all. And then from where do you get minus one? So look at this question here. And now tell me how the density matrix should look like if you are said that the microstate is such that the system is in down state.
So that Rho sigma is only the down spin one.
Okay. So it will be only this term.
Yes, ma'am.
Okay. So how will the matrix look like then? So this is in terms of the like in terms of the vectors, you are writing it in this way. But you have if you have to write in terms of a matrix, something like this, how will
Ma'am,
it look like?
1 minus 1.
Yeah, there lies the problem. Why are you getting minus? Like how are you getting -1?
Sorry, ma'am. So,
So how will rho look like? First, tell me in terms of this thing, how will it look like? You won't have this term. You'll only have this term. That's what you said, right?
yes, ma'am.
And what would be the coefficient? Like because it's only in this state. So
Ma'am, is it 1 minus 1 minus 1 1?
no. Okay. So see. Let us see how to do it. You are said that the only state that the system is in or the micro state is in down state, right? So that means your what will be your psi? What is your psi? Your psi is
Set of down. Uh,
yes, only
mm,
down. This is your psi. This is your psi, right? Now what is your rho? Rho is rho is defined as outer product of psi, right? So your rho will be only this. Is that correct?
yes, ma'am.
Okay. So now if this is rho, what will be the matrix form of this?
Ma'am,
So if you have this kind of product form, so this is your row 1 1, this is your row 1 2, this is row 2 1, this is row 2 2, right? These are the four matrix elements. Now you only have this term, right? Only this term. So you have multiplied, like you only have this term, meaning you have only the term which has multiplication of this and this, right?
so it will be 0 0 0 minus 1.
Okay, 0 0 0. Why -1? Like, like what is the physical,
Sorry,
like, why are you getting this idea of -1?
sorry, ma'am. It's,
No, no, don't be sorry. Like, think, like, why are you thinking that it should be -1? Is there a reason that is telling you? If there's a reason, then you should tell me the reason. Then we can discuss.
ma'am, I think it's in down state, so there must be a factor of minus 1.
But see, whatever be the state, what is what does the coefficient tell you? The coefficient tell you the probability of being in this state, right? The physical significance of the coefficient is the probability of being in that in this state, or the probability that it changes from. So suppose if you have this combination terms, suppose if you have something like this kind of combination terms, what does that tell you? So what does the coefficient of this term tell you? It tells you that the probability of if it can change from a down state to up state or a up state to down state, right? Now in this case, you know that your system is in down state. So you have only this term which includes only the outer product of the down states.
Yes,
So,
ma'am.
so this could be any two level system, right? You can have some maybe electron in a magnetic field, you have e to the power minus beta mu beta mu b and e to the power plus, like two states, mu b and minus mu b, something like that, right? So there, if you are said that you are in the lower energy level, will you think that there'll be a minus one? No, right? Because this term in the front or whatever you have here is actually the probability of being in that state, or being in the, or the probability of transforming from one state to another. So in this case, what is the probability?
One.
Right. So what should be rho? The rho should be, sorry, this is difficult. So the rho should be 0, 0, 0, 1, right? Correct, right? And then if you put this row in this format, you have up, down, column matrix, row matrix, and in between, if you put 0, 0, 0, 1, what you get is this, right? Clear?
Yes, ma'am. Clear.
Correct. And then suppose if you were set only in the up state, what you would have got? 1, 0, 0, 0, right?
Yes, ma'am.
Yes. And then in the last question, where here, when it was in a pure state, what did we get? We got some, so all the four matrix elements were non-zero. But this doesn't mean that it's a mixed state. It's a pure state because you can diagonalize them, and then you'll see that for some eigenvector, like when you diagonalize, you'll see that you have the eigenvalues, only one eigenvalue will be non-zero and the other will be zero, and all term. So in that basis, you will have only one non-zero element. In that basis, in this basis, you have four non-zero matrix elements. That's because that is not the eigenbasis. Clear, right? When you diagonalize, you go to the eigenbasis. There only in, if it is a mixed state, you can always diagonalize the density matrix. And when it is diagonalized, you'll see that only one eigenvalue is non-zero. And that corresponds to, and the corresponding eigenstate is the state in which your system lies.
Yes, ma'am. It is clear.
Yeah, yeah. Okay. Yeah, because this is a very important concept, so it should be clear. Okay, so I think that's it for today. So this is just an example. I did not give multiple examples because whatever you had done for the classical canonical case will be similar in this case. Only now the representation will be in terms of matrices. Okay, so that's it for today. No more doubts, right?
No, ma'am.
Okay, okay, okay. So thank you. We'll meet
Thank
next time.
you.
Yeah, thank you. Thank you. Okay, did I record or not? Huh? Okay.